Hello and welcome class. My name is Danish Zunnoon and I'm a senior physics lecturer for JEE and NEET division. So today, dear class, we are going to discuss another important topic from the chapter Rigid Body Dynamics, that is rolling motion. So what actually rolling motion is? So rolling motion is actually a combination of rotational and translational motion. Now, let's write it. Rolling motion, it is a combination of rotational and translational motion. Right? So before getting into the detailed analysis of rolling motion, if I ask you, can you give me an example from daily life of rolling motion? So yes, wheels of all the moving vehicles are in rolling motion. So now it is easier to visualize with rolling motion that the wheels are in rolling motion. So let's say this is the wheel of a vehicle and it is rolling. So if it is rolling on the ground, then it will have the translational motion with certain velocity. Let's say VCM is equals to V. Along with it, this whole wheel is rotating with certain angular speed omega about an axis which is passing through the center of mass and perpendicular to the plane of motion. Let me draw this axis. Suppose this is axis of rotation. So this wheel is translating as well as rotating on this horizontal surface. Now, if I split this motion into rotational and translational motion, that is, this wheel can be considered to be a combination of pure rotational motion about this axis, about which it is under pure rotational motion, plus the translation motion of the same wheel in which the center of mass is translating with certain velocity v. Right? So this rotational and translation, when combined together, what we obtain is rolling motion. Right? So let me mark velocities of some peripheral points of this rotating disc or wheel. So let me draw this horizontal and vertical diameter of the wheel. Now there are there are 4 points A, B. These are the end points of the horizontal diameter. C and D, you can write not C, let's say M and N, because C is taken for center of mass. M and N are 2 points which are the end points of vertical diameter taken on this wheel. Now, can you tell me what is the direction of velocity, instantaneous velocity rather, of these points M, N, A and D? So yes, for due to rotational motion, we know that velocity, that is tangential velocity of the particles, are given by V is equals to omega r in horizontal direction. Similarly, for this point B, it is in vertically downward direction, having same magnitude omega r. This is also omega r towards left. This point N, bottommost point, and this point A is having same magnitude of velocity omega r in upward direction. Right? Now, since this wheel is having a translational motion as well, so if here I am considering only translational motion, so for the same interesting points M, N, A and B, what are the velocity due to translation of this wheel? So this velocity is, since it is translating, so every point of that body will have same translational velocity as that of the center of mass. So this is V, V, V and V. Right? Now, since this wheel is in rolling motion, so this particle m will have a velocity which is having two components, one due to rotational motion, that is omega r, and the second one is due to translational motion, that is equals to v, velocity of center of mass. So I will draw these velocities here in the wheel in rolling motion. So let's say this point was M, N, A, and B. So this point M is having the velocity V plus omega r. This point will be having velocity, one component in rightward direction, that is VCM, another in leftward direction, that is omega r. Similarly, let me change the color first for the better clarity. For this point B, one component is towards right due to the translational motion, another is in downward direction due to rotational motion, omega r. So this point B is having velocity. Let me draw a neat picture, right? A neat diagram would be better to draw. So this is in pure rolling, right? This point is A, B, M, and N. So this point M will have two components of velocity, V plus omega r. This will be having omega r and V in outward direction. This will be having velocity of V and omega r in backward direction. This is V and omega r in upward direction. Now this particle M is having resultant velocity towards right. This particle B is having resultant velocity in this direction, and this is having resultant velocity either right or left. That will be depending upon the magnitude of V and omega r. And what about this? This is having a velocity of resultant velocity in this direction, right? So this point B will be instantaneously moving in the direction of its resultant velocity, neither purely horizontal or purely vertically downward. No, it will move instantaneously in its instantaneous resultant velocity, right? So these are the velocities of four different points. There are plenty of points lying on the periphery of this rolling body, but we have taken only 4 points for the purpose of better understanding, right? Okay. Now this rolling motion is divided into two categories. One is pure rolling, and the second one is rolling with skidding or sliding. Not sliding, slipping. Right. Okay. So let's begin with pure rolling. So pure rolling is that type of rolling motion in which a particular criteria holds true always. So let me try to develop that condition in pure rolling. So before that, I would like to let you consider the example of the rear wheel of the bicycle, right? Generally, a bicycle is having a wheel where number of spokes are coming out from the axle of the wheel and terminating on the periphery, right? And I can paint one of the spokes, sorry, I can paint it in red color, right? And I will mark it as 0 point, which is lying on the periphery of the disc, right? Or periphery of the wheel. This is point number 1, point number 2, 3. In continuity, let this point just before it is point number 10, right? This is point number 10. So if this wheel is rotating, it is in rolling motion. So this is velocity of center of mass V, and this is angular velocity omega, with which it is rolling on the horizontal ground. Now this wheel is rolling and translating, its axis is translating as well. Now, in the course of its rolling on the ground, these points at t is equals to 0, this point number 0 is touching the ground. After some time, this point number 1 will be falling on the ground, then point number 2, point number 3, point number 4, and so on. One after the other, these points will touch the ground, and suppose these points are having some color, just like let's say we stamp some paper, right? And the impression of that stamp is there on the paper. Similar to that, suppose these points are colored and they are able to leave their impression on the ground. So this point number 2, point number 3, point number 4, they will leave the impression. And at last, this point number 10 will also leave its impression on the ground when its turn comes, right? When it is rolling and one after the other. Let's say why I have colored this spoke, just to show you how many rotations are done by this wheel in this rolling motion. Suppose this wheel has reached here. Doesn't matter. And this is the radius r, and this red color spoke is shifted in upward direction. This C and this is 0.0, right? So I can say that angle rotated by this spoke is pi radian. Now, after that, when this wheel reaches here, or you can say the center of mass has reached at this point, and the wheel is has completed one complete rotation about its axis. So this red color spoke will again reach to its initial value, and this complete angle is 2 pi radian, right? When it happens, all the numbers up to 10, this 10 number is just before, it is marked just before this 0 marking, right? So if I ask you what is the length from 0 to 10 while you move along the circumference of this wheel, then it will be 2 pi r, perimeter. So can you tell me what is up to 10? Can you tell me what is this distance from 0 to 10 up to time t is equals to delta t? When this delta t time has elapsed, then what is the distance from 0 to 10? So obviously this is equal to perimeter, that is 2 pi r. This is perimeter 2 pi r, right? And if I ask you what is the translational displacement traveled by the center of mass? So obviously, sir, center of mass has traveled all along this displacement. You can see that this is a rectangle and opposite sides are equal. So I can say that displacement of center of mass is also 2 pi r. So interestingly, this equation holds true, that displacement is equals to 2 pi r. Now, if this displacement has taken place in delta t time, so if you differentiate this or divide this equation with delta t time, you will be having this value of VCM is equals to omega into r, where omega is what, sir? Omega is 2 pi by delta t, angular speed of this wheel about the axis of rotation, right? So this is the main condition of rolling motion, in which the body or the wheel rotates such that it leaves the impression like this. Suppose this is wheel and this is horizontal floor. So it is perfectly in contact one after the other. Why I am using perfect contact or perfect rolling? Because every point is touching the ground and then leaving the contact. The points of the wheel are not rubbing the surface in contact, right? I can show you a picture for the better clarity of rolling motion. I guess it is on slide number 1 or 2. Yes, here you can see that a vehicle has crossed on the road, leaving the impression of the tire. So you can see these perfect bricks that are impressed on the floor. So this is the case of perfect rolling. If it was not the perfect rolling, then you couldn't obtain this perfect bricks on the road or the impression of the bricks of the tire, right? So moving forward, this is the very important result that we have obtained right now, that velocity of center of mass is equals to omega r in case of pure rolling. Now we are going to reach at a very important conclusion, and in the form of a statement I will give you that conclusion. So what is that conclusion, sir? So this was our wheel, and we marked velocities of different points. If you remember, velocities of different points. Here, this point was N, I guess. This was A, B. R is the radius of this wheel. Suppose this is mass M. Doesn't matter. Now, can you tell me, for pure rolling, if this is velocity of center of mass V and this is angular velocity omega, then we know that for pure rolling, VCM comes out as omega into R, right? Now I will write velocities of these 4 points in this condition when VCM is equals to omega R. So this is V plus omega R. This is again V and then omega R in downward direction, and this point is having velocity translational V, and in backward it is omega R. Here it is V, Cm and omega R. Now the main point of interest is this point of contact at which this wheel is in contact with the ground. So can you tell me what is the velocity of this point N? So it is simply V minus omega R. This is resultant velocity. Now in case of pure rolling, for pure rolling, this condition holds true, due to which it becomes 0. So pure rolling is a condition in which the velocity of point of contact, instantaneous velocity rather, the instantaneous velocity of the point of contact with respect to the surface on which the body rolls is 0. So this is the main condition. And what is that condition? That pure rolling is a condition of rolling in which instantaneous of point of contact is 0, right? And the most important thing, it is 0 with respect to the surface on which it is moving or rolling. Sir, can you clarify this additional statement with respect to the surface? Yes. You can note it down and I can tell you why that statement is necessary. Suppose this is a platform on which this body rolls, right? It is having velocity VCM is V. It rolls with angular speed omega, and this platform itself is traveling or moving with uniform speed u. So can you tell me whether this body is under pure rolling on this moving platform or not? So I cannot say this just by seeing this situation. I need to have this knowledge of this velocity of point of contact. What is this velocity exactly? So see, this point of contact will be having a velocity component due to translational motion, that is VCM. Another one in backward direction, omega r, right? So the velocity of N with respect to ground, this is with respect to ground, it is V minus omega r, right? Now if I ask you what is this velocity with respect to the platform on which it is moving. Suppose this is platform. So it is velocity of n minus velocity of platform. So it is v minus omega r minus velocity of platform is u. If this velocity comes out as 0, then we can say that this body is under pure rolling on this moving platform. So what will be the condition for this? So the condition would be VCM minus omega r is equals to u on this moving platform. So it is not always the same case that VCM minus omega r must be 0. No, VCM minus omega r is having a velocity equal to the velocity of platform, or you can say that velocity of point of contact is 0 with respect to the surface on which it rolls. So that's all for today's lecture. I hope you understood it well, right? If you still have any confusion, you can let me know in the next class. So study, revise and practice. Thank you so much. Have a nice day.